folks, if you'll settle down, we're about to get started. It's a pleasure to introduce today's speaker, Steve Greenberg. So Steve is a linguist by training. I think he has a PhD from UCLA. But we've known him for many years as a linguist, of course, but also as somebody who cares a lot more about also just the intrinsic properties of sound and its neurophysiology and so on and so forth. We got to know, at least I got to know him many years ago when he did this transcription project where he phonetically transcribed spontaneous telephone speech. And how, I remember how a lot of these intuitive ideas or simple ideas I had about how you can transcribe something phonetically and what phones are changed, because he showed that spontaneous speech can be quite messy from, compared to this nice linear way of thinking about speech. And then since then he's done interesting work on other properties of spontaneous speech and on prosody and stress in spontaneous speech. And he's done some work on something that in engineering we call the modulation spectrogram, which characterizes speech perception. And he's done other things at UC Berkeley, where he headed a lab which works on speech, and he's a colleague of John O'Hala's, who some of you might know as well. Nowadays he wears two hats. He has a company called, I forget the name, Silicon Speech, there you are. And he's also visiting in Denmark at the Technical University. And today he's going to give us what I would call a classic Steve Greenberg lecture. He'll have many, many slides which will whiz by at high speed, but you'll still get a very good feeling about it in the end. He's going to talk about the essence of speech, or the essence of language. Steve.
Thank you, Sanjeev, for the introduction. What I'm going to do today is to give you highlights of what is ultimately designed to be the theory of almost everything with respect to spoken language. As Sanjeev pointed out, my original background was in linguistics and in phonetics at UCLA, but I also did a lot of work both at UCLA and at the University of Wisconsin on the physiology of human audition. And what I try to do is to sort of meld perspectives from many different disciplines, linguistics, computer science, electrical engineering, information theory, neurophysiology, to make things as simple as possible, but because life out there is very complex, not any simpler. And so I'm going to sort of describe an overall theoretical framework that I believe accounts for many phenomena in spoken language, particularly for English, but which I think also is likely to describe patterns in other languages. One of the reasons why I got into this was that I joined the International Computer Science Institute because I was interested in automatic speech recognition, and I was curious as to why the speech recognition systems didn't work better than they did. And the more I learned about speech recognition, the more I became convinced the problems were not with the engineering. They're actually quite clever, sophisticated algorithms, as you know. The problems were with the models of spoken language, which, in my view, did not accurately describe what I observed in the variety of studies that I'm going to describe today. And so I felt that the best contribution I could make to advancing the field of automatic speech recognition was to try to provide a different framework for which future generation models for speech recognition could be developed. Okay, so a lot of you, is there a laser pointer by any chance? I'll just use my pen, it's okay. In any case, you all probably know this, that this speech signal, spectrogram, frequency, time, pressure waveform is often described as a linear sequence of phonemes associated with discrete parts of the speech signal. So this is an N, this is an I, this is an N, etc. This linear sequence of phones is, I think, part of the problem with the current speech recognition systems. Within this framework, each frame of time is considered to be equal to every other frame. And I think this is one of the other problems, because perceptually, this is definitely not true. Some parts of the time signal are far more important than others, and we'll describe exactly what I mean by that. However, this type of analysis doesn't really require any a priori knowledge, which is why I think that it's so ubiquitous in speech recognition research. There are four principal problems, in my opinion, with this particular perspective. The first has to do with environmental variability, which many of you know. The left panel is the speech signal recorded close to the speaker's mouth. The right panel shows the same speech signal recorded somewhere back in the room. The reflections from the hard surfaces make this signal very different in appearance than what you see coming out of the mouth. The models of spoken language are largely predicated on what you see on the left, not what impinges on the auditory system of the listener, which is on the right there. So somehow, you need to somehow account for why listeners, as long as they're not hearing impaired, are able to decode the speech signal, given this is what they encounter, rather than that. Thank you. This one here?
Yep.
Great, thank you. Remind me to give it back to you. Okay. Okay, that's one problem. Another problem, as Sanjeev alluded to in his introduction, we've done phonetic transcription by hand. These were 3 linguistics students of 5 hours of spontaneous material from the switchboard corpus that was funded by the Johns Hopkins workshop. And what you can see is that you have huge amounts of variability for common words, and where the canonical pronunciation in the dictionary, and, is the 7th most common pronunciation, and it's 1/4 as common as the most popular pronunciation, which is an. This is not an isolated phenomenon.
I'm sorry, put it back, please.
Sure.
What is 7th most common?
So the canonical pronunciation, and,
Oh, I see.
is rank order 7, and it's about 1/4.
What does DCL stand for?
DCL, that's for closure. So sorry for the phonetic jargon there. This is
It's
designed.
of a D. I mean, is that why there is a D in front?
This is the canonical pronunciation. It turns out that the D at the end of a syllable, the coda part, there's very rarely a closure unless
I'm
you.
asking whether the CL has a D before it.
Yes.
Because it's a special closure of the
D.
sound D.
That is
I see.
correct.
So if it was N, then it would be MCL.
N's don't have closures in this sense.
P would be
But B or G or P, that's right. This slide is actually designed to impress and overwhelm you. You're not supposed to decode it in detail, as Fred just tried to do. Okay, so the point is that this is not an isolated phenomenon, that if you look at the 20 most common words in the switchboard corpus, which account for about 1/3 of the word tokens, you can see that there are dozens of different pronunciations typically, and that the most common pronunciation usually is only between 20 and 50% of the total. So variation in pronunciation is the rule, not the exception.
Pardon me, one
Please.
more question on
Sure.
the previous slide.
Okay.
The proof that it is the 7th is only the impressions of the people who transcribe, right? Consequently, it may not be like that from the signal point of view. It may be like that only from some perceptual point of view.
You're getting to very, very deep issues. This is why we chose highly trained transcribers, linguistic students. Also, we used not just the acoustics and the perception, we also used the waveform and the spectrogram. And so in this case, when we have a transcription of "an," we're fairly confident. I actually asked the students to be sure that there was no trace of a closure or a D. we also met weekly to make sure that they conformed to this. So unlike Ron Cole, who basically asked his transcribers to just base it on the spectrogram itself, we actually asked the students to use a combination of acoustics, in terms of the spectrogram, in terms of the waveform, in terms of the perception, as well as their knowledge of phonetics. So even though this may not be a perfect transcription, there is no such thing as a perfect transcription, I think it's not that far a depiction of the range of variation that you see. That's really what it's very variable. That's the main point. Okay. So challenge number 3 is that you have variation in time and in acoustic frequency of the units of spoken language. There's no single interval. There's no single unit like the segment that actually is able to provide a good characterization of spoken language. It's not just segments, it's not just syllables, it's not just words, it's not just in the acoustics. It's everything combined. And so this is actually a non-trivial problem about how to represent this. One example of what I mean is that this S here, this frication, this high frequency energy here, intrudes into the vocalic segment that follows it. So you have this overlap in time, illustrating the difficulty of assuming that each frame of speech can be associated uniquely with a particular phonetic segment. Another problem with the conventional acoustic phonetic segment approach is that in most spoken language you are in fact talking face to face. It's true not for switchboard where it was over the telephone, but it turns out that much of the speech in face-to-face interactions is decoded by virtue of the movement patterns of the lips and the jaw and the tongue in connection with the teeth, and that you have to take these visual cues into account to understand some properties of spoken language, as I'll describe later on, even if it's spoken over the telephone. Okay, so what do you do given this very messy situation, what seems almost hopeless to solve here? So I'm going to focus on what I call a multi-tier framework of spoken language, which is designed to describe how I think the brain processes spoken language under many different conditions. Also, it's designed to describe why the acoustic properties of speech are the way they are. Why is this important? I think because it's only when you understand the basic fundamental principles of a phenomenon, like nuclear fission or nuclear fusion, for example, that you can then develop technology that builds on that basic fundamental understanding to do something really amazing that otherwise is difficult to do. So atomic weapons would not have been possible without some deep understanding of fission and fusion. And I think the same thing holds for speech recognition, speech synthesis, and all other aspects of speech technology, that the deeper your understanding of the basic mechanisms, the basic structure, the more likely it is that you can develop technology that is really robust and reliable under a wide range of conditions. Okay, so let me summarize my talk, and then I'm going to go back and highlight a few parts of it. I don't have time to go through every slide, so I'm not going to do as Sanjeev says, as I'm going to whiz by, because I want you to understand some points very, very well. And I welcome people like Fred in interrupting and saying, I don't understand what you mean by this, because I think that's exactly the right approach. So if you don't understand something, please raise your hand and please tell me to explain. So what I'm going to try, you have a question about that? No. So what I'm going to suggest is that the syllable, rather than the phone, is the most basic. It's not the only, but it's the most basic organizational unit of spoken language. For example, the patterns of pronunciation variation, some of which I showed you earlier, really are much more easily explicable in terms of the syllable than they are in terms of the segment. There are some other levels as well that we need to take into account. Moreover, the syllable carries what I call prosodic weight, what some people call prominence, what some people call stress accent, that affects the manner in which the phonetic constituents within the syllable are realized. So in this framework, you can't consider the phonetic composition of a syllable, the phonetic segments within an utterance, without understanding the prosody, because the two are sort of flip sides of the same phenomenon. So the behavior of these syllabic constituents, what I call the onsets at the beginnings of syllables, the codas at the ends of syllables, and the nuclei, which are usually vowels, which represent often peaks of energy in the syllable. They're each quite important. They each have their own phonetic character, and they each respond differentially to the prosodic weight of the syllable. In some sense, syllable position, whether it's at the beginning or the ends of syllable, is almost as important as what this segmental identity is. And this actually stems from an auditory perspective. Auditory neurons are much more responsive to the beginnings of new events than to the endings or even at the steady state peaks. And that's because the auditory system and other brain regions have essentially evolved to detect new events. Much of the information is therefore encodable in terms of neural discharges at onsets. So it makes sense that much of the energy from an auditory perspective would be localized at the onsets, not in the nuclei and certainly not in the codas. Okay, so we're going to examine the microstructure of the syllable. What I mean by that for this sample word nap, you have three segments, N, A, P, in terms of manner, voicing, and place. Manner is the mode of production that determines how the airflow goes through the vocal tract. For nasal, that means that the air is coming through the nasal tract as well as through the vocal tract. A vowel, it means that there is lots of energy. There's no real tight constriction between the tongue and the upper palate. The stop, as its name implies, means that you have a complete occlusion at some point in the vocal tract. For the P, it's at the lips, and not surprisingly, that's where the energy is low. In terms of voicing, this pertains to whether the larynx is voiced or is vibrating or not. The vocal folds are vibrating. And you can see in this example here that you have voicing for the first two segments, and ostensibly you have lack of voicing in that final segment. And place of articulation refers to the locus at which that constriction occurs. So for the N, it occurs in what's called the sort of medial part of the vocal tract, the alveolar ridge contacting the tongue. For the P, it's the two lips coming together, and for the vowel, it's at the front part of the vocal tract, and so on. And I'm going to show you lots of examples of what I mean by that. Manner of articulation, that's whether it's a stop or a nasal, etc., is most closely associated temporally and in some other parameters with the classical concept of the phonetic segment. So in this multi-tier framework, the phoneme really doesn't exist. The phonetic segment really doesn't exist, but you can actually describe what people refer to as segments in terms of its manner of production. Moreover, each manner, and stop, fricative, nasal, vowel, is associated with different energy levels. So vowels, peak energy, stops, fricatives, low energy, nasals and liquids, intermediate energy. The significance of this is that acoustically one can describe without any a priori linguistic or phonetic knowledge these patterns of rises and falls of energy in terms of something called the modulation spectrum, which I'm going to describe in much more detail later on here. The spectrotemporal profile, this three-dimensional representation of the energy pattern of this disyllabic word 7, is essentially the impulse response of the modulation spectrum here. So you can actually use the modulation spectrum to reconstruct the specific energy patterns across time and frequency. Okay, place of articulation, that's where the maximal constriction occurs. Front, back, or somewhere in between, is typically considered to be the feature that is lexically most discriminative. In other words, it's the feature that phonetically is most important for distinguishing words, but there's something, excuse me, it's the feature that is most closely corresponding to the formant patterns. But also, it's phonetically very, very stable across languages. I'm sorry, I thought I turned it off. Acoustically, place of articulation is the most vulnerable. And so ironically, the phonetic feature, place of articulation, which is extremely important for decoding consonants, is also the feature that acoustically is the most vulnerable to background noise. The formant transitions, which are closely associated with place of articulation, suggest that in fact that these formant transitions, contra the conventional wisdom, are not the most perceptually relevant part of the speech signal. That some other parameter is probably more responsible for place of articulation information because they're so easily degraded. In my view, the stability and reliability of the place of articulation cues stems from the fact that you basically have bimodal representation of place of articulation. My colleague Ken Grant at the Walter Reed Army Medical Center has done a number of studies that demonstrate that about 95% of the visual cues are in fact providing place of articulation information for consonant identification. In noise, visual cues provide up to 10 decibels of gain in signal-to-noise ratio relative to the acoustic signal alone. Okay, so that means that the visual cues ultimately can't be neglected. And I think you had a workshop project here about 3 years ago where you focused on audio-visual speech recognition. I think this is exactly the right approach because eventually we'll have cameras ubiquitous in all the machines that we interact with. Voicing in this framework is not a segmental feature, but rather a syllabic feature. It's one that essentially provides important information about the syllable structure. It emanates from the vocalic nucleus and it spreads forwards in time into the coda of the syllable and backwards in time into the onset. The importance of this is that voicing can be used to deduce certain aspects about syllable structure. It's also what gives the syllable its energetic framework. The most intense parts of the speech signal are voiced. The least intense are usually unvoiced. Moreover, voicing is related to prosodic prominence. Voicing is extremely sensitive to whether the syllable is prominent or not. So it is the patterns of interaction among these different articulatory acoustic feature dimensions, along with prosody, that actually specify the phonetic composition of any span of speech. And so what we're going to look at is essentially how these units interact with each other under a variety of different conditions. So the articulatory acoustic features of manner, place, and voicing are governed in this framework by prosodic prominence, as well as their position within the syllable. That's why you need to have information about all of them. But why should this be so? It's not arbitrary. It's because the prosodic pattern you see in spoken language largely gives you a guide as to where the information-laden parts of the speech signal are. And so the more intense, the longer duration the syllables, the more likely it is that those syllables are carrying important information required to decode the speech signal. So in some sense, you can actually get a window onto the underlying semantics by analyzing the prosodic structure, and that's reflected ultimately in the very fine phonetic detail that phoneticians traditionally just attribute to biomechanical constraints or other unknown factors. This is a very Freudian view of the speech signal. There are no accidents. There is no sort of randomness, or very little, that in fact even those very fine details in fact are giving you certain aspects of meaning and nuance and shading of intention that can be interpreted by the listener. Therefore, it is ultimately information and lexical discriminability that governs the detailed phonetic properties of spoken language. What this means, I think, for speech recognition is that the extent to which you understand what the significance of those fine phonetic details are, and the extent to which you have classifiers that can reliably decode them, you stand a much better chance of being able to accurately interpret the acoustic stream to identify, to recognize the words. Okay, so ultimately, this type of framework implies that you first, even though you have a bidirectional process for coding, that initially you have to do some sort of coarse energy analysis. This is done probably at the level of the auditory cortex. And yesterday, in Eric Young's group at the medical center, I saw some very interesting cortical data that are very consistent with neurons essentially picking off these long duration modulation patterns, and other neurons picking up the acceleration and velocity, what you call the delta and double delta features of the speech signal. And so you first do, in this framework, a coarse analysis where you identify the number of syllables, the syllable patterns in terms of which ones are prominent and which ones are less prominent. You only then start to do a detailed time frequency analysis to figure out what are the manner constituents of the syllables, and only after that do you then decode in detail in terms of getting place of articulation. And it's only when you do this coarse to fine analysis that you are actually able to decode the fine phonetic detail. Often the context in which the particular speech occurs gives you some clues, but in cases where you have no real context or where they're proper names, you do have to do some sort of bootstrapping along the lines like I show you. In that sense, this is more like what image processors do, where you first do a coarse analysis and only later go into the very fine details. The important thing is that the syllable essentially is the nexus that acts as the interface between the acoustics and the phonetics and the phonology and the higher levels of prosody and morphology and the syntax and ultimately meaning. And so even though the syllable is not the only unit, it is a key unit in that it actually acts as sort of the way station for lower level units that are governed by their behavior within the syllable, and the higher level units that influence how that syllable is realized in terms of its prominence, duration, things of that sort.
Steve?
Yes?
Are you suggesting on the previous slide that the that the model is coarse defined and might be globally decoded at all these levels at once, or that the processing is actually coarse defined regardless of how much background noise there might be to mess up your reconstruction of, say, the prosodic accent at the first step.
So someone asked me a few weeks ago why I thought it was unidirectional. And my answer was, I don't think it is, but for technology applications, you have to bootstrap somewhere. And therefore, if you're developing an automatic system, you first need to do the coarse characterization in order to do the fine. I think that once you get into an utterance, it is bidirectional. But I think that unless you do that coarse syllable level analysis first, the ability to do the fine-grained analysis is very difficult. Experiment done 35 years ago at UC London, Hindi speakers were recorded speaking English words. And so character becomes collector. Then these same Hindi pronounced words were presented to native speakers of English, and they were just asked, what words do you hear? Just write them down. So the word character, which is pronounced collector, is transcribed as director. And so this suggests that, at least for English, people first look at the prosody and only later look at the fine phonetic details. So the segments in that example would say character, but in fact the prosody is more consistent with the word director.
That example doesn't say anything about the order in which people process, though. What
No.
it says is that one
It does
set
not.
of features outweigh the other in the decode performed by the human.
When you see the data I'm going to show you, I think you'll understand why I think it's necessary to first have a coarse analysis, because your ability to interpret these fine spectral temporal details requires some knowledge of what the syllable position is and whether that syllable is highly stressed or not. So it actually reduces the complexity of the decision by a lot. But you're right, it doesn't prove it. And obviously we have pathways that go both up and down. But when I show you these data, I think that you'll understand why I think that it's essential to first be able to characterize the syllable structure and the prominence pattern before going into the phonetic decoding. Because the phonetic decoding can vary a lot. But knowing the syllable structure, knowing the prosodic prominence associated with that syllable enables you to essentially reduce the uncertainty. In my view, the acoustics are inherently ambiguous. There's no deterministic auditory decoding of anything. Speech, music, anything out there. You learn to associate acoustic patterns with certain objects. And that's true for speech. And so you have an inherently ambiguous signal. It's not completely random, but you can't actually interpret what the meaning of these formant patterns are without some knowledge of the syllable structure and the prosody. Okay? This is one of the reasons why speech synthesizers that don't incorporate prosody sound so terrible, and why they're often so difficult to understand. They have the segmental information, but they don't have it within the proper syllable structure or the prosodic structure. Okay, so in my view, I think that what you need to develop better speech technology is to have a multi-tier, what I call an entropy-based analysis, where you have to take the entire semantic context into account. Because even with the syllable and the prosodic information, having some notion about the topic and the range of possibilities of the words is very useful for decoding. Okay, so what I do in the second part of the talk is that I focus on a few topics that I think are of particular interest to the audience. And then I sort of go on to the next topic. So the intent is not to go through 100 slides, but to actually go through those that I think are really important. this is one that I think is quite important because the energy arc provides, I think, a principled mechanism for understanding why different segments occur in the order they do within a syllable, for any language, I think. So this is what's called the sonority hierarchy, going back to Otto Jespersen in the 1900s, but which I think actually reflects cortical processing constraints. Basically, the energy arc reflects both production and perception. You just make the assumption that the auditory system requires arcs of energy at frequencies roughly between 3 and 10 hertz. It turns out that auditory neurons are specialized in even non-humans, in marmosets and cats, to process events that occur roughly between about 3 and 20 hertz. If you make that assumption, then syllables essentially become the waveguide for these energy arcs. The reason why fricatives and stops occur at the beginnings or at the ends and not in the middle is that they are low energy inherently. The idea basically is that the reason why we have syllable patterns the way we do is that it's essentially an automatic way of guaranteeing that you have rises and falls of energy with time constraints that are commensurate with the modulation spectral processing that occurs in the auditory system here. Okay, so the importance of the energy arc for intelligibility is as follows. It's been noted that in intelligible environments, the modulation spectrum has a profile like this. It has a peak at around 4 or 5 hertz. That's shown here. Clear delineation between syllables. When you have reverberant environments where reflections from the surfaces add energy back into the troughs of the syllables, the boundaries between the syllables become blurred, and that's reflected in a reduced magnitude of the modulation spectrum. It's reflected in a reduction of the peak from about 4 hertz to 2 hertz or 1 hertz. This particular example is still intelligible, but if you reduce the magnitude further and you decrease the peak further to about 1 hertz, this speech becomes unintelligible. What this says is that there's something very important about syllable and syllable structure that's important for decoding spoken language. So what does the energy arc reflect linguistically and phonetically? You can hand segment, in this case 15 minutes of spontaneous speech, it's Japanese, and transform it into modulation spectral units. So 200 milliseconds represents 5 hertz, 10 hertz represents 100 milliseconds, and so on. And then compare it to the modulation spectrum of the same speech signal, you see that the two closely correspond. What this suggests is that modulation spectrum essentially represents syllables. So in my view, the energy arc provides a more principled basis for understanding the phonotactics of spoken language, because it puts it within a neurological framework that's also an information theoretic framework. Essentially what it says is that vowels, high energy, fricatives and stops, low energy, nasals, intermediate energy, liquids and glides, energy levels in between vowels and nasals. And so it essentially says that the reason why we speak in the order we do in terms of those segments is because we have evolved to speak in terms of arcs of energy here, and that the phonotactics of any language conform to this. Okay, so it's a very cold-blooded information theoretic perspective where you essentially are using the phonotactic structure of the language to get the acoustics to conform to a pattern that the brain can decode. Pure and simple, yes?
I just wonder, could you go back a slide or two?
Sure.
I lost what this modulation spectrum curve is.
I'm going to talk about that in another slide
so we
or
shouldn't
two.
understand what that curve is other than it looks like the one on top. I mean, it's sort of reflective of something like the sonority hierarchy.
Okay, let me answer your question in detail. This reflects the oscillation of energy in the speech signal, as you see here. This is the full spectral bandwidth signal. In reality, what you do is you partition the spectrum into narrowband channels. In our case, usually about 1/3 octave, which is the critical bandwidth for auditory processing. And what you do is you can extract, for example, the Hilbert envelope, the Hilbert transform version of the envelope to be able to assign a frequency to the modulation of the carrier. And in other words, you can quantify this oscillation of energy in a fairly precise way. There are different ways of doing this. And I don't think that's really relevant to this talk, but the point is that this energy arc allows you to understand why you have consonants alternating often with vowels, and why when you have consonant clusters, the clustering order is of a certain domain and not of another order. In other words, you have a non-arbitrary pattern in spoken language that you can associate with the acoustics and with constraints of neural processing. This allows you, if you transform it into the speech recognition domain, to say, okay, we have some unknowns here. We have some low-intensity consonant. We have a vowel, and we have something in between. That something in between can only be a few things in terms of a segment, in terms of manner of production. It has to be something of intermediate energy, which means it has to be a liquid or a glide or a nasal. It can't be anything else. And so the idea is that you have certain principled pattern constraints that enable you to interpret these energy patterns, because you've learned that this is basically speech. You can be 200 yards away from someone speaking on a hiking trail. You can't decode, but you know it's speech because the temporal properties of that signal are unique and distinctive. You know that's a human talking, even though you can't decode the specific phonetic constituents from that distance. Does that answer your question? So.
It would be nice to know, again, on the slide that Bob was asking about.
This one?
How you compute
okay.
Each of the points on this graph.
Okay, I can tell you. Basically, what you do is you transform the modulation spectral axis. It's essentially like a Fourier analysis with one very important exception. It's more like a filter bank. You have 1/3 octave channels that you compute the energy. Those 1/3 octave channels are associated with different time intervals. That's actually crucial. And therefore, at 5 hertz, the analysis window is roughly about 200 milliseconds. Because you're using fairly narrowband channels, it means that the interval associated with energy analyzing lower frequency modulation frequencies is shorter than the cycle of the modulation interval itself. So instead of having 1 second long at 1 hertz, 2 seconds long at 500 milliseconds, etc., it's actually shorter. So it actually depresses the amount of energy that is apparent in the low modulation frequencies. This is very important because if you did a normal Fourier transform with like a 1 second interval, you'd have a low pass filter, and this peak here would actually appear as just a little blip. The reason why I believe this is the right way to do it, and this is the way that Hartgas and Stanikin originally did it, is that the integration time constant for auditory system, for the visual system, for the motor system is 200 milliseconds. This allows the brain to dissociate those parts of the modulation spectrum close to DC and 1 hertz, which are associated mainly with distance and with loudness, but which is not associated with the message, from the message containing parts of the modulation spectrum which occur above 3 hertz. So does that answer your question? Okay. It's actually a fine detail that most people don't appreciate, but it's actually crucial for understanding why you have this band pass function rather than something that's low pass. I'm going to decide what's important for this audience and what's not. So I'm supposed to finish by about 5:30. Okay, we started a few minutes late, but I'm not going to try to hold you much beyond that. So let's talk about prosody. So utterances are composed of syllables of variable prominence or stress accent, is shown here. One of the things that we've noted, and some of you know this work, is that if you look at the vowel system from the perspective of what we call the vowel triangle, you notice that you have a relatively even distribution of vowels. This is E, I, A, I, ow, O, and U. A little bit of a reduction in the back vowels, and U. That's important for another point, which I'm not sure I'll be able to talk about, but keep that in mind. This is for heavily stressed syllables only. If you look at the unstressed syllables, you see a different pattern. It's very rare that you have vowels like A and I and A, the low vowels, or the diphthongs in unstressed syllables. It's mainly I, and So in other words, in some sense, the vowel system and the prosodic system are one and the same. They're highly related to each other. Okay? If you think it's this way for English, Danish is a purely prosodic language where the vowel system really is a prosodic waveguide. Languages differ in terms of how much the vowels are sensitive to prosody. English is somewhere in between Spanish, where it's not very sensitive, and Danish, where it's extremely sensitive. The important point here is that you have correlations between vowel identity and the prosodic valence of the syllable. This is one reason why I think that the syllable and prominence comes first, because it actually allows you to interpret what that vowel is likely to be. This shows you the contrast between the heavily stressed vowel system and the unstressed vowel system. It turns out that the durations of the low vowels tend to be longer, they tend to be louder. It turns out that prominence is closely associated with duration and with energy, as well as with vowel quality. So in fact, it's consistent with the notion that syllable prosody and vowel systems are basically just alternative ways of looking at the same thing here. I'm flipping through to see what I want to talk about here. I'm going to skip this part because I want to conclude on something that I think will be interesting to you. Okay, it's pronunciation variation. Okay, so there's a differential weighting of syllables depending upon whether the segment is at the beginning or at the end, or is the nucleus here. And you really have to take this into account in being able to interpret the acoustics. And so I think this is extremely important for acoustic models for speech recognition, because if you know where you are in the syllable, and you know whether the syllable is stressed or not, and we have automatic classifiers that can do this reliably, then it allows you to more accurately decode the phonetic constituents. So one way of demonstrating that is to show that if you analyze the deviations from canonical pronunciation. So this is from the switchboard corpus. This is manual transcription, where we compare what the speakers actually said in terms of these manual phonetic transcriptions with what the canonical dictionary representation of those words are. Here you see that the less the prominence, so none means that this is unstressed syllables, the more likely you are to have deviations from canonical pronunciations. This is not surprising. However, if you look at the different types of deviations from canonical pronunciations for substitutions, where instead of saying pen, someone said pin, for example, which is common in Southern California, you can see that the probability of canonical pronunciation, it's much greater for the unstressed syllables relative to the stressed syllables. However, the codas, it's relatively insensitive to the prosodic valence, and for the onsets also relatively insensitive. So in terms of substitution deviations, it's mainly in the nucleus, and the prosodic valence of the syllable has a huge impact. For deletions, in that example I showed you earlier where and becomes an in the most common pronunciation, that's a deletion. You can see that that's mainly in the codas, the ends of syllables, and that unprominent syllables, it's much more likely to be deleted than for stressed syllables here, and it has relatively little impact for the nucleus and for the onset. And these 13% largely are DH sounds that are mainly in function words. That's a separate category. And so basically deletions are mainly in the coda, substitutions are mainly in the nucleus, and they're extremely sensitive to the prosodic valence of the syllable. So when you look at the deletion patterns for the coda consonants, what you see is that the centrally articulated consonants like T, D, and N are much more likely to be reduced or deleted than consonants that are produced by the articulation of the lips or the velar closure at the back of the mouth here. And the question is why? And that goes back to the vowel system that I showed you earlier. Notice that there is a relative paucity of vowels in the back part of the vowel space. What this means is that the second resonance, which is the key resonance for perception, basically is mainly between 1500 and 2500 hertz for the overwhelming majority of the vowels, whether they're in stressed or unstressed syllables. It turns out that the frequency locus for the TDs and Ns, for the coronals, is in this same frequency region. What this means is that you can reduce or delete that consonantal segment at the coda and still have an intuition, still have an impression, still have a residue that there is an alveolar consonant there as well. And so there is an interaction between the acoustic patterns of the vowels and the consonants that gives you some insight as to why the coronals tend to be deleted and not the bilabials and the velars. The other thing that's interesting is that if you look at the statistical distribution of place of articulation in the onsets and in the codas of syllables, you see something different. A relatively equal distribution in the onsets, but in the codas, about 3/4 of the consonants, in fact, are centrally articulated. They're alveolars, usually T, Ds, and Ns. When you see a distribution like this, it usually means that it's associated with something predictable and there's relatively low entropy there. And that's consistent with what I told you earlier about the auditory system cares much less about the ends of events and is much less capable of analyzing the detail of the ends of events than it is for the onsets. And so it makes sense that most of the information phonetically is concentrated in the onsets of syllables, not in the codas. Okay, I'm going to summarize. So the syllable rather than the phone in this framework is the most basic organizational unit of spoken language. I don't see any other way to account for the patterns of pronunciation variation, some of which I've described today. The syllable carries what I call prosodic weight, which we know is prominence or accent, that affects the specific manner in which the phonetic constituents within the syllable are realized. That's why you need to know something about the syllable structure and the prominence. Otherwise, you can't really unambiguously interpret those acoustic patterns and associate them with these abstract segments. The behavior of these syllabic constituents, the onset, the nucleus, and the coda, differ dramatically from each other and are very sensitive, but in different ways, to prosody. The microstructure of the syllable can be delineated in terms of voicing, manner, and place of articulation very efficiently. So matter essentially is close to what we call the phonetic segment. The energy arc reflects basically modulation, spectrum, and cortical processing constraints. Place of articulation, that key lexically discriminative dimension, is inherently transsegmental that binds vocalic nuclei and codas and onsets together. However, the form and transitions that are normally associated with the place of articulation features are actually very vulnerable to background noise. They're not the most robust part of the speech signal. The visual cues usually occur in concert with the acoustics and therefore disambiguate. Therefore, models that are focused purely on form and transitions with only acoustics, I think, is bound for trouble. And I think this is one of the reasons why speech recognition systems that focus purely on the form and patterns don't do that much better, don't do any better than the conventional ways, because they're not that important. Voicing emanates from the nucleus, and it's a syllabic, not a segmental feature. You can account for many things across languages and historically that I haven't had time to describe if you accept that premise. It's the pattern of interaction among these articulatory acoustic features at the syllabic level interacting with prosody that give the specific phonetic definition for utterances. However, it is information reflected in the prosody that actually determines the specific phonetic realization of spoken language. Therefore, it's ultimately information that has to be known to be able to predict the specific phonetic properties, and vice versa. If you know something about the specific phonetic properties, you can get a glimmer as to what the information content is connected to that speech. Thank you very much for your time. So I have many other slides I could have shown, but I wanted to give you the essence of this, but this has lots of implications for speech technology.
Okay, so you've made the point that you need to pay attention to the syllable, but then you've also indirectly shown that choosing the syllable is a little bit arbitrary, because you've shown that different syllables will behave differently depending on the position they have with respect to stress.
Yes.
Right, so that was the argument you gave for choosing the syllable, is that different segments will behave differently in different positions in the syllable. The same argument applies
Yes.
in moving from the syllable on up. So
Yes.
extrapolating from your argument is just, one would just conclude that you have to pay attention to everything. Is that correct?
No, you don't have to pay attention to everything.
But you have to go beyond the syllable. You've shown
Yes, yes. So what you can do, I mean, some people ask this question in terms of, well, what do you mean by syllable and how do you basically parse the syllable stream? You don't have to actually define the syllable boundaries with precision. I doubt that humans do this either. It turns out that what you can do is to pick off the vocalic nuclei, which are usually fairly easy to pick off with automatic means. And we have done this automatically. We train manner of articulation classifiers, and it turns out that the vocalic classifiers are about 95% accurate. And what you then do is you analyze this vocalic part of the syllable. You know how many syllables there are. You can estimate the prosodic prominence, because it turns out that 3 parameters, duration, normalized energy relative to syllables, syllable nuclei within a 3-second context window, and the spectral envelope associated with that vocalic segment give you about 90% of the optimum performance of the automatic classifiers. And the automatic classifiers for stress accent labeling are as good as that derived from a human. So this is actually the output of an automatic system. And when I've shown this to the students who did the manual labeling upon which this was based, they were really stunned at how well it did. So in other words, we can actually, with automatic means, do labeling based purely on those vocalic nuclei as good as a human transcriber can do. And therefore, I think that you don't really need to know much more than that about the syllable. Then you can sort of work backwards. Now that you know where the peak is, you can then work back to figure out what the likely constituents are preceding and following it. And I think this is actually what people do. You basically go for the peaks first, and then you work backwards. Particularly for the onsets, and the codas probably come last. And that's probably needed only part of the time to lexically discriminate when things are ambiguous. Often it is unambiguous. Yes?
Just curious, whether these aspects of speech have remained the same for the last couple thousand years, or do you think there's been some evolution?
Speech hasn't remained the same over the last 10 months, no less the last 10,000 years. There have been studies shown, Bill Labov was the first one to demonstrate this about 40 years ago. It turns out that the pronunciation patterns of generations growing up in the same area are different from each other. In fact, people, as they grow older, pronounce things differently than when they were young. There were recordings of the Queen Elizabeth's Christmas speech, recorded over 50 years. And the vowel system that she used in 1955 is actually different than what she used in the year 2000. So the sound patterns of language actually are very dynamic, very fluid, and you have huge changes over very short spans of time.
But you first started out saying there was this invariant, or these
Yes.
several invariants that were...
There are a few.
There are a few. So what about them?
Okay, so this
Have
is
they changed?
not that much. And so from my talk, what would you predict would be the stable constituents of the speech signal? So it would be at the onsets of stressed syllables, maybe, because that's important. And place of articulation, as I've mentioned before, is lexically highly discriminative. So you would predict that in genetically related languages, like German and English, for example, or Dutch, that cognate words that have separated by time depth of 1,500, 2,000 years, those features, the place of articulation, particularly in stressed onsets, would remain relatively stable. And this is true for the Indo-European languages. That's the stable part. The prosody is very labile among dialect regions. This is why Southerners are so difficult to decode by people who grew up either outside the United States or even in other parts of the region. The prosody varies hugely, but what allows a speaker from the Northeast to interact with someone from Atlanta, perhaps with difficulty, is the fact that you have certain stability in terms of the onset consonants in those stressed syllables, plus learning to compensate for some of the variability. But if those onset consonants were not stable, it would be very difficult. And it turns out, in a slide that I skipped for reasons of time, I show that the distribution of place of articulation in both the coda and in the onset is not sensitive to prosody. It doesn't matter whether it's in unstressed or stressed syllables. It's the only phonetic feature dimension that is not sensitive to prosody in that sense. And that's consistent with prosody being the main apparent reflection of variability. So the place where you have the essence of the phonetic identification for lexical discrimination is unaffected by that. So that means put a lot of emphasis in your consonant decoders at the onsets of syllables. Very important, much more important than in coda consonants or in the vowels. Much more important.
You still have to deal with phonemes at the end of the day, though, because...
You're right, it is the end of the day.
Right. So,
And you're not going to let me leave before I deal with them.
so the inventories of consonants that you get in coda position and in onset position are not independent. there is a notion of inventory that
I know there's this concept.
well, there's also the fact that it's not the case that an onset and the vowel will bind together and constitute a unit. It's pretty well the case that any consonant can combine with any vowel at the beginning of the syllable. So at the end, you still have to deal with inventories of consonants and vowels. It's not as if
In broad
there's an
classes,
inseparable unit.
yes, but remember the energy arc. One of the nice things about the energy arc
How could I forget?
is that it allows you to deal with this, let me go back, in terms of signal processing and acoustics. So you can combine things as long as they actually can transition appropriately in terms of those energy modulations. If they can't, they don't. It's sort of like flipping concatenative synthesis on its head in terms of speech production. And so that, to my mind, is the utility of a concept like the energy arc in the sense that it's not arbitrary. It's not like any sound can join with any other sound. There are constraints, but they're not arbitrary. And that's what the energy arc tells you, exactly what those constraints are. And more importantly, it tells you why. And therefore, you can then extend that insight to other conditions which the theory was never intended to account for. So on the basis of this theory, I can actually predict where the McGurk effect, which is the combination of visual and acoustic blendings, occur, where it fails. It's not published in the literature because no one publishes negative results. But the theory actually predicts where it fails. So I call my colleague Ken Grant and I ask him, is there any place where it fails? Because the theory predicts that in places where you have unambiguous acoustic cues for place of articulation, like you do for the alveolars, for T's and D's, basically the visual cues cannot move it. And so I asked Ken, are there any places where it fails? Long pause, yes. What are they? T's and D's. How about vowels? Because it also predicts that oo, when combined with like B, also there's very little form and transition there. Therefore, it's unambiguous. Therefore, a goo visually can't move that percept acoustically. And that's exactly what happens. So Ken says, ooh, no one uses ooh. I say, why not? Because it doesn't work with ooh. And so this theoretical framework can predict many otherwise weird things, both perceptually in terms of the nature of spoken language, in terms of like the pattern of voicing in German, the difference between German spoken in the north and the south, for example, and the voicing of the S or not, and so many other things. It has to do with the prosody and the infiltration of voicing into the onset of the nucleus. And yesterday I asked a native German speaker at Johns Hopkins Medical School whether this makes sense. And she said, yes, basically it is a sharpness, it is an emphasis on the beginning that you get that Z. And so there are many otherwise seemingly arbitrary linguistic facts that are actually explained within this framework. That's why I have some confidence that at least the essential outlines of this is accurate. Some of the details are no doubt wrong. It's incomplete. But since it's so powerful, there's got to be something here, and I think you've got to be able to use these constraints, perhaps in Sanjeev's new maximum likelihood sets, to essentially supplement the statistical basis that you use for speech recognition systems now. It's got to help if it's done right.